Well, welcome back again to the fourth of the five little mini lectures on interesting wave behaviors. So the first three were interference, reflection, and diffraction. Today, on this one, we're going to focus on refraction. And then the last one that I'll make is on the Doppler effect. So I'm going to claim that refraction is probably the one that's most common and relevant to your life, although you probably aren't aware of it. So I'll describe that here in a second. And like I've done on the other ones, I'd like to show you what refraction looks like first on my little virtual simulation of the ripple tank. And that will help us to better understand when I describe what it is and show you how to draw it. Okay, so let's take a look at the virtual ripple tank for refraction. So I'm going to help you focus on what's going on here during refraction, but I do need to warn you that what I'm going to show you will also include some reflection. So I'll point that out first. But here's what I've done. I've set up my ripple tank, and I've added in this triangular region here, and let me tell you why it's there. That represents a part of the ripple tank where the water is more shallow. Okay, so we're going to see with refraction, this is what refraction is. We have one part of the medium, in this case water, that's got a little different property or characteristic as the other parts. So for water, the main thing that affects the waves is the depth of the water. So we saw this before when we did the gizmo, and we did it with a spring or a slinky. We could stretch out and make more tension in the slinky. We could also change the density of the slinky. Those were properties of the spring or the slinky that changed how the wave moved. In particular, it's the wave speed that's going to be different. So you'll see here when it gets to the dark blue region that the speed of the waves will be different. Okay, so we're going to make plane waves here just like we've done before, and you'll watch them. And let me point out first the reflection. You see this reflection? It's heading rightward. Follow my mouse here. That is something that I can't really help, but waves will reflect off a boundary like this as well as refract. So what I want to focus on now is look at the dark blue. Do you see that the waves in here are certainly moving more slowly? I'm going to restart it each time. Just look at the wave speed here for the original medium, the light blue medium, versus how slow they're moving here. Okay, so that's one thing that I want you to notice. The waves are slower. Because they're slower, they also tend to stack up on each other a little closer. So that's a measure of the wavelength. So you see how the spacing between the bright areas is shorter or smaller than it is in the other medium. The other thing we have going on, by the way, is interference. So we're seeing like three different things happening here. When the waves, the original waves, interfere with the reflected waves, we get that kind of weird wave pattern. So here again, look at the wave speed here and the wavelength, the space between them, and how much smaller the wavelength here is because of the slower speed. And then the last thing, the third kind of important thing I want to point out is look at the direction that these plane waves are moving. They started out moving straight down on my screen, but now there's a little bit of leftward motion as you look at it, in addition to still being mostly downward. So three things I want to focus on. The speed changed, therefore the wavelength also changed, and the direction of the wave was altered slightly. Okay, that's really a key description of the three things that happen with refraction. Now, I will tell you, even though I'm not going to demonstrate this, if this weren't at an angle here, if it were just flat, like in line with the plane waves, we would still get the change in the speed and still get the change in the wavelength, but we would not see the effect, the bending effect that you have here. Okay, so let's go to the page. You should be on page 10 in the notes packet, and we'll get this written down the way we want to. Okay, so here's our refraction page. When we describe what it is, I'll try to keep it short. There's a lot more we could write if we wanted all the detail. This is the bending of the wave direction when a wave moves into a different medium. So I'll remind you, the medium is what we call the material that the wave is going through. So in our virtual ripple tank, it would be water. In the case of like sound waves going through the air, the medium is the air, okay? So we're not really going to a different medium because it's still water, but there's something different about it. So we can change the depth of the water, and that effectively makes it a different medium, okay? Let me put a comma here instead of a period. So I want to point out, we are changing the speed and wavelength. So the direction changes because the speed changes. Now, do particles do this? You might remember, I told you when I started these 5 that only one reflection shares a property with particles, like tennis balls will reflect off a wall, just like waves do. But waves will refract, although particles do not, okay? I'll come back to the real-life examples. I'm going to show you how we draw this. So this is like the one that we had that I just demonstrated with my virtual ripple tank. So we're going to show these same waves. What I'm doing is I'm continuing. You see where these waves are here? The waves that are still in the original medium travel straight down. Okay, that's the original motion here. And it's still traveling straight down here. It's when they're in this, let's actually write this, the shallow area. That way you remember what it is when you look back on it. And because you can't see it on the picture, let's just write it here. It's shallow and therefore a slower medium for these waves. So I'm continuing these little darker areas here, but I'm going at a little bit of an angle. And because of that, these are actually closer together than the ones over here. Not a lot, but we certainly saw that in our animation. And then let's show the direction. See how I'm angling these arrows just a little bit? So I'm showing that they're not going straight down. Okay. All right, pause here if you need to finish drawing anything. You don't have to be an artist, but you do want to hit those key points about the direction and the way the waves move before you call it good. All right. Then we'll take a look at what happens when we have a rounded boundary, kind of like we have here in this middle one. Now I've got something similar here, except this my shallow medium is just a kind of an elliptical shape, we call it, sort of an oval. And we're going to see a different effect here. So let me show you what happens when we get the plane waves moving. Still see a bending effect, but you see how it bends differently now. And all these waves, as they come out, they focus. See where my mouse is pointing right now? They focus right there. Now, again, we're getting a mess of reflections and interference going on here. So I'm going to keep clearing the waves so you can kind of see. All right, here's again, a little reflection going on. But here's the first wave that enters into this shallow medium. And it's kind of curved, almost that matches the curve of the ellipse, but not quite. And then let me continue it on. Okay, and then when it comes out, it curves even more and comes to, you may remember when we saw this with reflection, it comes to what we call a focal point. Okay, so let's go draw this so we can get a good picture of what this looks like. So again, we get this curve inside here. All right, kind of a frowny face if you look at that. And then it curves even more when it comes out. And then let's label this focal point. So it's almost like we can steer these waves to all meet each other at a point. In fact, we really build these what we call lenses so that we can steer waves to be where we want them to go. Since I just mentioned that, we actually would call this a lens. That is the best real-life example I can think of. Lenses. And I'm talking about the lenses that everybody is born with in their eyes. You have a natural lens in your eye. And then some of us need additional lenses because our lenses have stopped doing things quite like they were supposed to. And what the point of the lenses in our eyes is for is so that the light waves that hit the eye can come together and focus on the back of the retina. I'm not trying to give you too much of an anatomy lesson here, but we need those light waves to focus at the back of the eye. And sometimes the lens is not shaped quite right, either from birth or maybe as you age, I should say, maybe as I age. And so we need a little assistance to bend those light waves in just the right place so that we can focus those light rays. So glasses or contacts do that same thing, all right? So this is like the lens you have in your eye. Now, on my glasses, I need one eye to bend the light waves more, and so I have a convex type shape. And the other one is bending it too much, and so I need a concave shape. Now, I don't have this on my simulation, but let me show you what happens when we get to a boundary that's shaped like this. Instead of curving kind of frowny face, we curve more smiley face, if you will. And then curve even more than that. And so instead of bringing the rays together, we're actually spreading the waves apart. Maybe I'll show this here, the difference. These waves are headed to the same direction, this focal point, whereas these waves are spreading apart. Okay, so we can have all kinds of interesting shapes. And they actually do that. If you really closely examine like somebody's lenses and their glasses, they're not like this or this. They're actually a very complex shape so that we can bend them just how the eye needs it. Mine are actually called bifocals. There's actually two different lenses. One for when I see distance off the top of my eye, and one when I'm reading, I read closer to through the bottom of the glasses. There's actually a different prescription there. Okay, some of you may have the same kind of thing. All right, but golly, we've gone about 12 minutes here, and that's certainly enough. So I think we've seen everything we need to see. Let me zoom out here so you can make sure everything looks kind of the way that I have it on mine. If you need to go back and review anything and rewrite anything, listen to things, hopefully you did not just fast forward through this and do it on mute, but you need to hear all of this explanation that goes with the writing. Okay. All right. Thanks for watching. If you need to see one more, Doppler effect is the last of the 5 wave behaviors.